All right, so for those of you who missed Tuesday's class, we started talking about molarity. So what is molarity, you ask? So molarity is defined by taking the moles of a solute, and if you recall, a solute is the thing that gets dissolved into a solution. So for instance, with a saltwater solution, sodium chloride, the sodium chloride would be the solute, and in order to get molarity, which is a type of concentration, we are going to divide that by the liters of solution. And perhaps to be more explicit here, I'll actually write out liters for you so that you don't forget that that's what that means. So we take the moles of a solution, moles of the solute, and divide it by the liters of the solution. Pretty straightforward. This is just a simple algebra problem. Now, we're going to have to manipulate some of our data a little bit. So, for example, let's say that I have 85.0 grams of potassium chloride. And we're going to put that into let's say a 400 milliliter solution. And we're going to make that those two zeros significant by placing our decimal after it. So there's our 400 milliliter solution. So 85 grams of KCl of potassium chloride into a 400 milliliter solution. Now, this causes a problem because we don't need grams of our solute, we need our moles of the solute. So we have to think back to first semester, our conversion from grams into moles. So we can start with our 85 grams. We're going to convert this into moles. So in order to cancel out our labels, we're going to take grams of potassium chloride. That's going to go on bottom, and we're going to convert that into moles of potassium chloride. So this is all review from first semester. And the numbers that go along with this, because it's a conversion factor, we're saying that 1 mole of potassium chloride is equivalent to some number of grams of potassium chloride. And if you remember, the way to figure that out is we'll go to our periodic table and we'll find that potassium has a mass of 39.098. And we're going to add that to our mass of chlorine, which has a mass of 35.453. Okay, so that gives us a total mass of 74.551. Now I could use all 5 significant figures, but because I'm only working with 3 significant figures, I can trim that down a little bit. I'm just going to put 74.55 grams of potassium chloride, so that will work for us. And so since this is going to cancel out, our grams of potassium chloride will cancel out. That will leave us with moles of potassium chloride, which is exactly what we want because of our number of moles of solute that we're looking for in our problem. So once we solve for that, we'll get a mass of, a number of moles of 1.14 moles of potassium chloride. Now, this makes it really simple to use because we have our 400 milliliters, we have our 1.14 moles of potassium chloride, so we're just going to plug that into our equation up here. We have our moles, which would be 1.14 moles of potassium chloride, and we also have our volume. But Mike, you say, we have 400 milliliters, and we need it to be in liters. So this is a simple conversion. We know that every 1 liter of volume is equivalent to 1,000 milliliters. So we just move our decimal place 3 places. And so that will end up resulting in a 0.400 liter solution. Remember, those zeros are important. They are significant. That is measured out to 400 liters. We're not about 400 milliliters. We are exactly 400 milliliters, which is the equivalent of 4/10 of a liter. Remember that significance does play a role and it will change your answers. So once we solve that, we're going to take our 1.14 moles. Let me type that into my calculator here. And divide that by our 4/10 of a liter. And that ends up resulting in 2.85 moles per liter. And so what we end up with is we can actually change that into a different label. Moles per liter is the same as molarity. So we end up with 2.85 molar solution of KCl. Pretty straightforward. Okay, so we can, if we have our mass or our number of moles, we just divide it by the volume of the solution. So that makes it really, really easy. Now, could we take that and change that around? Absolutely. I'm going to get rid of all of this. And what if we have to change it around? And instead of figuring out the molarity, let's pretend that we are given the molarity. So like what happens a lot of times in labs, we're asked to have a certain molarity of a solution. So let's say that I need a 3 molar solution. And since salt is something that we work with frequently, we'll just use regular table salt, sodium chloride. And so let's say that I need a 3 molar solution of sodium chloride. Now, you're probably not going to need a liter of solution for your lab. So we might have to make a smaller solution. So let's say that we need 75 milliliters instead of a full liter. Now, we have the experience of being able to convert between different types of units, but molarity is one that we aren't quite familiar with, or we're not as familiar with. So what we can do is we can convert this 3 molar solution into moles per liter. So that would look like 3.00 moles of sodium chloride divided by 1 liter of solution. Okay, so hopefully you're seeing that those are equivalent. So the 3.00 molar sodium chloride solution is equivalent to 3 moles per liter. All we're doing is we're rearranging so it has a different type of label, but they mean the same thing. It's just a concentration. Now, once we have this, we can use our prior knowledge in order to pull this in and be able to make a measurement of how much solutes we're going to have to weigh out. Because I can't go back and just be like, all right, I'm going to get my 3 mole scoop and take that out. That's not going to work for us. So I need to use some sort of unit that I can actually measure. And so we've had a lot of experience using grams, so that's probably going to be our most efficient way to measure that out. So thinking back to first semester, we know that moles of sodium chloride are going to go on bottom because that matches our label previously, so those are going to cancel out. And we know that we want to get that into grams. So I'm going to put grams on top. What I want to get rid of is on bottom. What I want to keep is on top. So I have grams per mole. So that is referring to molar mass. So 1 mole of sodium chloride is equivalent to the molar mass of sodium chloride. So this is where we have to go back to the periodic table. We look up sodium. Sodium has a mass of 22.99 grams per mole. And then we add that to chlorine with a mass of 35.453 grams per mole. So let me plug that into my handy dandy calculator here. And what I get is 58.44 grams per mole. So, looking at this, we know that we want to get grams. We want to be able to measure the grams of sodium chloride out. So we solve. And what we get is to three significant figures because I have three significant figures for the 3.00. I have four significant figures for the molar mass. So that means we have to default to the 3. That ends up being 175 grams, but these are the only two that cancel out. We're still left with liters. So this is 175 grams per liter. This is really still our concentration. This is to tell us that we want to weigh out 175 grams to make a 75 milliliter solution. What this is telling us is that if we wanted to make a liter of solution, we need 175 grams. So we need to take a slightly different route. What we can do is we can set this up as a proportion. And so what we'll take is 175 grams over 1 liter, because that is essentially the fraction that has been given to us in our labels. For every 175 grams of salt, we're going to get 1 liter of solution. And so by making that a proportion, which you should have learned in algebra all those many, many years ago, is we can figure out how many grams of sodium chloride do we need in order to make a 75 milliliter solution. Now we can't come over here and just write in 75 milliliters. We need our labels to match up. So we are going to put, instead of 75 milliliters, 0.075 liters, because again, we know that 1,000 milliliters is equal to 1 liter. So I move my decimal place 3 places. Now we cross multiply. So that's going to end up resulting in 1 liter times X is equal to 175 grams times 0.075 liters. We need to get X by itself. Now the 1 isn't really relevant, but just to make sure that all of our labels end up canceling out, we take 1 liter and divide that out, so these are going to cancel. But what we do to one side, we have to do to the other. And so our liters are going to cancel out over here. And so what that leaves us with is X equals, well, we're going to take 175 times 0.075, and that gives us 13.125 grams. So if I need to make 75 milliliters of solution, you just use molarity in order to calculate how many grams of salt you're going to need in order to make that 3 molar solution. Okay, it's no different than what we've been doing. It all comes back to problem solving skills. Taking the information that you have and being able to manipulate that into something that you don't have. So hopefully we're feeling comfortable with that. If you're not, we have lots and lots of other practice problems that we'll be using in class, but I just wanted to make this an introduction right now. But leading into Wednesday, I'm going to put both Tuesday and Wednesday together. Wednesday this week, what we ended up doing is we jumped over to a problem where we were applying the idea of molarity to a situation where you're going to have to figure out how much of the copper 2 sulfate are you going to need in order to get a certain amount of something else. Okay, so the problem that we have is 1 volume of 0.500 molar solution of copper 2 sulfate is needed to react with an excess of aluminum to provide 11.0 grams of copper. So we have a problem. We have a task. So again, we're going to be using those problem solving skills. Okay, the same skills that we're going to use for any other situation apply here. The only difference is, in this case, we're dealing with chemistry. But starting off, one of the first things I've always asked you to do is identify what are you asked to find, and then what is the information that has been provided to you. So in this situation, they have said that you need to find how many milliliters. Sorry, that was supposed to be a question mark there. How many milliliters? And if we want to be really, really specific, we can say how many milliliters of 0.500 molar solution of copper 2 sulfate. So our formula for that is CuSO4. Do we need in order to make, well, that's the thing that's been given to us. That would be 11.0 grams of copper. So we have the things that we have been given. We know what we're trying to find. And so now it's just using all the skills that we have been given in the past, or that we've learned in the past, in order to apply it to a new situation. So we have copper, but we also have copper sulfate, and we need to get between the two. So in our stoichiometry unit, we learned that in order to go between two different types of things, two different types of molecules or types of atoms, you're going to have to use a molar mass. A mole ratio. So in making that mole ratio, first of all, we're going to have to convert our grams into moles. That just makes sense. So just like we did in our last set of problems, we're going to convert from grams of copper into moles of copper. And just like before, we know that 1 mole of copper is equivalent to whatever the periodic table says that was. And keep in mind that was found out, the molar mass is figured out over lots and lots of experimentation. So our mass of copper is 63.549. We're only dealing with 3 significant figures, so 63.55 should be sufficient. So now we're in moles of copper. But we don't want moles of copper. We want moles of CuSO4, of our copper 2 sulfate. So in order to cancel out our moles of copper, we're going to put that on bottom, and on top we have our moles of copper 2 sulfate. And if you think back, one of the issues that we have is, in order to make this mole ratio, we need a balanced equation, which we obviously don't have in this situation. However, you do have the skills in order to make that equation out of what's been provided to you. So in the problem, it tells us that you have copper 2 sulfate. Obviously, we're going to have that. And it is needed to react with, so we have copper 2 sulfate. And it is going to react with, that's our indication that we're going to have a plus sign, an excess of aluminum. So that's going to be plus Al. To provide or to form, okay, so that's our indication that there is going to be a reaction occurring. So I'm going to put in my arrow. 11.0 grams of copper. Copper is just simply Cu. But that's not where our equation ends. Excuse me. Because of the law of conservation of matter, we can't just get rid of that aluminum. We can't just make that sulfate ion just disappear. So we need to account for that as well. So those two are also going to bond together in a single replacement reaction to form aluminum sulfate. And I'm sure some of you looked at that and you're like, oh, all right, aluminum and sulfate, they'll go together. Aluminum is positive, sulfate is negative. Those just go together and it'll be AlSO4. But keep in mind, we have to balance that. Okay, we have to make sure that those charges cancel each other out. Aluminum has a +3 charge, whereas sulfate has a -2 charge. So that means that you're going to need 2 aluminum ions for every 3 sulfate ions. Now we have a balanced a balanced compound here. But our overall equation is not balanced. So we're going to have to go over here and take a look. So we have 2 aluminum, so we'll put a coefficient of 2 over here. We have 3 sulfate ions, so we're going to put a 3 here. and then that means that we have 3 copper ions. So now that we have a balanced equation, we can go back to our stoichiometry and plug in our coefficients of 3 and 3. Okay, those two right there. Okay? So, still not done. We want to find out the milliliters, not the number of moles of copper sulfate. Copper 2 sulfate, excuse me. So this is our new step. We have another piece of information that we haven't used. We need to take a look at this molarity. But using molarity the way that it is not something that really works for us. So we're going to have to manipulate it some. Right, so we have another step. We know that moles of copper 2 sulfate are going to be on bottom because that's going to allow them to cancel out. And then on top, that's the part that we don't necessarily know. But we do know that molarity is moles per liter. And so what's going to happen here is I can put liters on top, but I want my answer to be in milliliters, so I can convert that into 1,000 milliliters. So I can just skip a step. But then it comes back to what's on bottom. Well, this is what tells us is on bottom. We have a 0.500 molar solution, so we're going to have a 0.500 moles of copper sulfate, copper 2 sulfate, for every 1,000 milliliters. From there, we can just simply solve the way that we've solved the entire year. So I'm going to take 11 divided by 63.55. I can multiply and divide by 3, but those cancel out, so I don't even need to worry about those. Times 1,000, and I'm going to divide by 0.500. And what I get is up to 3 significant figures. I have 346 milliliters of 0.50 molar copper 2 sulfate. Okay, fairly straightforward. We're going to get some more practice on this week, but hopefully that catches you up so far in case you missed the last couple days.